Hey everybody, Trey here. Welcome back to another video. Today we're going to talk about a parameter that is very important in deciphering which areas may be more likely to produce tornadic storms than other areas in a given setup. And we've talked about this parameter before in our forecast discussions and in the SKU-T and hodograph series. I'll put a link to that series in the description below. But today we're going to take an in-depth look at this parameter because I like to call it kind of the cheat code of tornado forecasting. It really can discriminate between non-tornadic and tornadic environments, or at least environments that are maybe more likely to produce tornadic storms than other environments. And this parameter is called 3 CAPE. And as the name suggests, it is the CAPE, or measure of instability, in the lowest 3 kilometers of the atmosphere. So basically, it is a measure of the low-level instability. So let's talk about 3 CAPE from a meteorological perspective here. So this is our atmosphere. Here's our surface. Let's say this is our 3 kilometer level here. So if we have high values of CAPE in the lowest 3 kilometers, in other words, we have high 3 CAPE. And when I talk about high 3 CAPE, generally a rule of thumb is looking for values of 3 CAPE that are greater than or equal to 50 joules per kilogram. And the higher the 3 CAPE, the better. The higher the 3 CAPE, the more unstable your low-level atmosphere is. So if we have high values of 3 CAPE here, that is going to mean that our 0 to 3 kilometer layer, that lowest level of the atmosphere, the lowest layer of the atmosphere, is going to be very unstable. In other words, air is going to be able to rise very rapidly or very efficiently on its own. Air is very buoyant in that level. Well, so let's say we have a thunderstorm, a supercell thunderstorm, move into this environment of high 3 CAPE. Well, if we have any sort of spin near the surface, whether it is induced by a boundary or whether it's ambient vorticity created by strong low-level shear, which we can find through our hodographs, then you're going to have an environment that is much more likely to foster tornadogenesis than in an environment of low 3 CAPE, because this spin near the surface can be very efficiently stretched into the vertical and is able to make that connection between that rotation aloft and the rotation near the ground much more efficiently than in a low 3 CAPE environment. So that's why 3 CAPE, I like to call it kind of the cheat code of tornado forecasting, because if you have high 3 CAPE and you have supercells moving into an environment of high 3 CAPE, those storms are going to be much more likely to produce tornadoes, much more likely to undergo tornadogenesis with large low-level shear than in an environment where you do not have large 3 CAPE. Now, 3 CAPE on its own is not going to tell you whether or not you're going to see higher tornadogenesis chances or not. You have to have this spin near the surface. And again, this is going to come from strong low-level shear. So usually strong turning of the winds, strong veering of the winds with height in that lowest 3 kilometer layer, which is going to create strong ambient low-level shear. Or you have ambient vorticity along a surface boundary. So basically a stalled outflow boundary, a slow-moving frontal zone, that you have, of course, winds. For example, if you have an outflow boundary here, winds are going to be basically, for example, out of the east or easterly here to the north of the boundary, out of the southeast to the south of that boundary. That creates enhanced low-level shear, enhanced vorticity along that boundary, and that spin can be stretched into the vertical in a high 3 CAPE environment. So let's go ahead and look at a bunch of examples here. We're going to take a look at some cases here, several different cases that I've picked out highlighting the importance of 0 to 3 kilometer CAPE in tornado forecasting. So this was a sounding from April 22nd, 2020, near Ardmore, Oklahoma. This is a RAP sounding from 21Z. This is in proximity to a couple of tornado-producing supercells near Springer and Medill, Oklahoma. This is a photo here showing the very large tornado that occurred near Springer on that afternoon. This was the proximity sounding to that environment. So you can see here a very large overall CAPE, very strong instability here. But take a look at our 3 CAPE values, and this is where it's going to be plotted on our SPC soundings and our model soundings as we have here. 3 CAPE of 206. And remember, we said our 3 CAPE values, we're generally looking as just a kind of a rule of thumb for values greater than or equal to 50 joules per kilogram. And the higher, the better. So when you see values over 200 joules per kilogram of 3 Cape, that is a very extremely unstable low-level environment here. And you can see this is our 3 kilometer layer right here. So you can see we have very fat Cape in that lowest 3 kilometer layer. And again, if you don't really know how to read these soundings, take a look at that SKUT and hodograph series that is in the link below. But basically here we have very fat Cape, very large instability here in the lowest 3 kilometers of the atmosphere. And again, what is that going to do? Well, when we have ambient vorticity, ambient spin near the surface, in this case we have nice turning of the winds, of the low-level winds with height. You can see here from the hodograph, nice long looping low-level hodographs here. Well, that's going to take that spin and efficiently stretch it into the vertical, enhancing the tornadogenesis processes. And as we saw very rapid tornadogenesis on this day with multiple very large, strong tornadoes. So an easier way to look at this is on the SPC page. If you go to the SPC mesoanalysis page and you go all the way to multi-parameter fields, and then go down to surface to 3 kilometer Cape and surface vorticity here. This is the kind of the holy grail product that I like to use basically on every single chase, because wherever you have heightened 3 kilometer Cape, which is these red contours here, coinciding with strong low-level vorticity or surface vorticity here, which are these blue contours, whenever those coincide, you have a better chance for supercells in that environment to produce tornadoes. Because one, we have strong low-level shear or strong low-level vorticity, and we also have strong 0 to 3 kilometer Cape. So we have very strong instability in the lowest levels that is going to be able to stretch that vorticity into the vertical very efficiently. So let's take a look at our April 22nd case here. So this is our April 22nd case, 0 to 3 kilometer Cape and surface vorticity here. And as we go through the day on this afternoon, here you can see as we go through, that surface Cape and vorticity really builds. And what do you know, by 22Z we have kind of a bullseye there in southern Oklahoma. Nice low-level vorticity we saw there on our sounding. We had nice low-level curvature in that hodograph. And that kind of that highest 3 Cape is kind of focused there from southern Oklahoma to North Texas. So we have kind of an overlap there in far southern Oklahoma. And what do you know? Same locations where we had a nice localized sort of tornado outbreak there in southern Oklahoma, right on the nose of that 3 Cape and surface vorticity maximum. Let's go back to our soundings here. This is another example. This is the Winterset, Iowa case from March 5th of this year, March 5th, 2022. Now, not quite as noticeable here on our sounding, whereas on the Springer case, we had a very visually, you could just tell visually that the 3 Cape was going to be very high. Nice fat Cape there in that lowest 3 kilometer layer, yielding 3 Cape of over 200. In the Winterset case, not as much 0 to 3 kilometer Cape here. You can see it's kind of a little bit skinnier here. Here's our 3 kilometer layer. So kind of skinnier low-level Cape here, but we do have 3 Cape here approaching 100 joules per kilogram, 88 joules per kilogram here. So more than adequate for assisting in tornadogenesis. And what do you know? Very strong turning in the lowest levels of those winds with height. Nice curvature in the hodograph here. And this was able to produce an EF4 tornado that was in progress for over 60 miles here near the Des Moines area. That did lots of damage and unfortunately killed a few people near Winterset, Iowa. Well, let's take a look at our 3 Cape here. This is our 0 to 3 kilometer Cape map here. And so we're going to take a look here at southwest Iowa. You can see that surface vorticity builds in, as does that 3 Cape by late afternoon. Our bullseye right there in southwest Iowa, approaching 100 plus joules per kilogram of 3 Cape. Nice spin near the surface. That spin was able to be stretched very efficiently. And what do you know? Our tornado track here, all located in southwest Iowa, right in that 3 Cape and surface vorticity bullseye. Another case here, typically where this 3 Cape kind of rule works really well is in your cold core setups. And what when we mean cold core, it's when you have a 500 millibar trough, kind of a 500 millibar closed low here, and you have your surface low kind of tucked up underneath that surface, that 500 millibar low. So you have very cold air aloft, and that usually helps increase the low-level instability quite a lot in these cold core setups. And this was an example from January 30th, 2021 in far northeast Oklahoma near the town of Wann, W-A-N-N, Oklahoma. So you can see here, this was a proximity sounding there, 19Z on January 30th, 2021. You can see that the overall CAPE is not that great at all. It doesn't extend very high into the atmosphere like we saw with some of our other cases, our more warm season cases here. But you can see all that CAPE is very much concentrated in the lowest levels of the atmosphere. Here's our 3-kilometer layer. Very nice low-level instability here with a 3 CAPE value of 140. That's very, very high. And again, notice our hodograph here. Very strong low-level shear. Nice looping hodograph. Nice turning of the winds. Veering of the winds with height in the lowest levels of the atmosphere. We were able to see some cold core tornadoes out of very low-topped supercells on this day. Here's a picture of that, of one of those here. So let's go back to our mesoanalysis here. This is for January 30th, 2021. Once again, notice that maximum right in northwest Oklahoma there. Very big 3 CAPE bullseye right there in northeast Oklahoma, with some surface vorticity to boot. And what do you know? Our tornado reports were up there in far northeast Oklahoma as well, right on the Kansas border, right near that bullseye. And just talking about that cold core for a second, if we go to our 500 millibar chart here for this day, you'll notice we have a very strong 500 millibar trough here. Not quite a closed trough as we see in most 500 or most cold core type events, but very strong trough here at 500 millibars. Lots of cold air aloft associated with this trough. And if we take a look at our surface low here, you'll notice that surface low, very strong surface low, right up there tucked under that coldest air aloft, right up here kind of on the Kansas-Oklahoma border. And you often see that 3 CAPE kind of axis, that instability axis, wrap up into that surface low. And just east or northeast of that surface low center is where tornadoes are most favorable in those cold core type setups, right under that cold pocket aloft. And that's why we get often heightened 0 to 3 kilometer CAPE in those instances. So another kind of event to look at here, we talked about this in one of our recent videos on the October 6, 2010 northern Arizona tornado outbreak. Same kind of concept here. Your overall CAPE, not very strong, only 460 joules per kilogram of CAPE here in the entire profile, and you can see that very small, sort of very low-topped convection here. But notice our 0 to 3 kilometer CAPE value, 151 here. This is our 3 kilometer CAPE, 3 kilometer level right there. You can see very fat CAPE in that lowest 3 kilometers there. And take a look at this hodograph. Very strong low-level shear here, very strong turning of those winds in the low levels, so very strong surface spin. And that was able to be stretched into the vertical very efficiently here with multiple tornadic supercells in the morning hours and early afternoon hours of October 6, 2010, including this EF2 tornado that went through the town of Belmont. So once again, let's take a look. This was our 3 CAPE and vorticity plot for October 6, 2010. This is at 12Z, right as those tornadoes were happening. You can see not a super big, noticeable bullseye here, but definitely a localized maximum here across northern Arizona. And as the early morning hours and as the morning hours went on into the early afternoon, we did have an EF3 tornado up here near Tuba City, Arizona, right on the northern end of that 0 to 3 kilometer CAPE bullseye there. And with that amount of low-level shear, tornadoes were a good possibility on that date. And as you see, coinciding with that 3 CAPE bullseye, right there were the bulk of our tornado reports there in northern Arizona. A couple more examples to go through here. This is another cold core case here. A little bit, this was a warm season case, May 29th, 2019. This was definitely a warm season case here. And you'll notice the overall kind of fat CAPE there. 3 CAPE value of 247 here. This happened near Pocahontas, Iowa, in kind of northwest Iowa there. But take a look at this. This is our 3 kilometer layer here. Look at all that instability in the lowest 3 kilometers here. Very sort of fat CAPE there. That's why we get such a high 0 to 3 kilometer CAPE value here. 247 is pretty much off the charts here. But one thing you'll notice about this hodograph here is we had very little low-level shear to deal with. You can see the winds here kind of wonky, not much turning in the low-level winds there in those first 3 kilometers there. So the hodograph was quite straight, not really looping, not a lot of clockwise curvature there at all. So not a lot of ambient vorticity here, but that doesn't mean that this 3 cape was going to go to waste. If we look at our surface map here, this is the surface map from May 29th, 2019. You can see here as we move on through the late morning hours, you can see our surface low is up here in kind of the sort of South Dakota, Nebraska, Iowa triple point region there. And we had a surface boundary, kind of an old outflow boundary from morning convection, kind of an effective warm front sort of thing. You can see easterly winds here to the north, southeasterly winds here in southern Iowa, definite kind of boundary there, and this would lift to the north and aid in the low-level shear. So we weren't dealing with necessarily strong low-level shear, but it was greatly enhanced along this outflow boundary, kind of effective warm front feature. And you can see here that it kind of washes out a little bit in the afternoon. We have nice surface low there in northern Iowa, northwest Iowa, and kind of that leftover boundary there here helped aid in enhancing the kind of weak ambient low-level shear along that boundary. So that 3 cape was able to take that vorticity, concentrate along that boundary, and stretch it very nicely here. So northwest Iowa, here's our 3 cape and vorticity plot, and you can see that as we go on through the afternoon, we kind of get a nice bullseye there in far northwest Iowa with some, you can see the blue contours there, surface vorticity right along that boundary ahead of that surface low was high, was enhanced. And there's our 3 cape bullseye. And what do you know? Lots of tornado reports there in northwest Iowa right near that bullseye. Another thing to note here, you can see we do have kind of a secondary mode here in East Texas. And you can see from our storm reports there, we had several tornadoes there in northeast Texas near the town of Canton there on that day. This was more of a kind of warm sector ahead of the surface boundary, kind of warm sector deal that we often see in the southeast. And I'm not going to go over that setup in depth, but you can see here lots of tornado reports there, and we had a nice 3 cape bullseye there. The low-level shear, the hodographs were much more clockwise curved, much more veering of the winds with height down in this area, and we had that 3 cape bullseye there, and that's where all the tornado reports were in that kind of secondary setup there as well. So this was a photo from that day, nice tornado there. And this also works for land spouts. And now I plan on doing a land spout forecasting video in the future. But 3 cape is a very important parameter in land spout tornado forecasting. Of course, we know that land spout tornadoes are non-supercell tornadoes, or non-mesocyclone tornadoes. So they result from spin that is near the surface, little eddies near the surface, generally located along a boundary or kind of convergence zone. Those can be stretched into the vertical, and you really need strong low-level instability, steep lapse rates near the surface to help stretch that vorticity into the vertical under those maturing cumulus cloud bases. This was an example from May 28th, 2018, the Land Spout Fest in northeast Colorado. So this was our sounding here, very strong instability here, almost 3,000 joules per kilogram of cape. Look at our 3 cape value here, 179. Lots of instability concentrated in that lowest 3 kilometer layer. We do have a little bit of ambient vorticity here. This was our rap sounding from Lyman, Colorado, near Flagler, where those land spouts happened. A little bit of ambient vorticity, but we were dealing with a surface boundary here. You can see convection in northwest Kansas sent off an outflow boundary here, kind of led up into these storms, and this was our storm of interest here that produced several land spouts, including several that were in progress at once, and a couple that were actually pretty stout. This was a picture of one of them as we were driving toward it there, near the town of Cope, Colorado. And you can see on our surface map here that there was definitely a boundary in play. Easterly winds in far northeast Colorado. You can see that boundary still pushing out storms here in northwest Kansas. We're kind of reinforcing that boundary, but the western portion of it kind of stayed there and helped set the stage for a land spout outbreak there in northeast Colorado. So vorticity was enhanced right along that boundary. And we had very strong low-level instability that day. You can see here is our 3 kilometer cape and vorticity map. As we go forward in time there, you can see that bullseye there right in northeast Colorado with some of that surface vorticity along that boundary. And of course, lots of tornado reports there in northeast Colorado where that overlap happened. So that's going to do it here for this video. Again, this is a very important tool for forecasting tornadoes, especially on the day of when you're in chase mode and you are trying to forecast which areas might be a little bit better for tornadoes than others. Trying to look for those 3 Cape and surface vorticity overlaps and maxima are going to help you out quite a bit. Now, it's not a hard and fast rule. You can get tornadoes in kind of weaker, low-level instability, but generally you want to be looking for that where you have a co-location of strong low-level shear, whether that is from a surface boundary where you have little spin, little eddies along the surface boundary that can be stretched into the vertical, or you have strong low-level shear from kind of low-level directional and speed shear. In other words, strong clockwise curving hodographs, where that is co-located with strong values of 3 Cape, meaning that, again, that spin near the surface can be amplified and stretched into the vertical very, very efficiently. That is where you're going to see supercells in that environment tend to have a better chance of producing tornadoes or undergoing tornadogenesis than supercells in kind of a low 3 Cape environment. And again, 3 Cape doesn't matter unless you have low-level shear, because if you don't have anything to stretch into the vertical that's spinning, you're not going to get tornadoes. So it's as simple as that. Again, I like to call 3 Cape and surface vorticity the cheat code because it can really discriminate between tornadic and non-tornadic environments when all other parameters are there. So with that, thanks for watching. We will see you in the next video.